engineers have difficulties of obtaining good quality samples of certain materials, pareha ng sand ug soft clays, for laboratory testing, and some tests are considered and best done in boreholes on site. In materials whose coarse grain size prohibits taking samples large enough to test in the laboratory, the only way to obtain these test results is by testing on field. So, good day to all, and we are the Group 6, and we will be discussing this test on field, the geological field test and measurements. So next is the outline of our topic. So ang chapter nga among i-discuss ron kay na divide into 7 lessons. So the first lesson is the test in boreholes, and under this test in boreholes are the resistance to penetration, the strength and deformation test, the permeability test, and the measurements of the in situ stress. So the next lesson is the test in large diameter boreholes, shafts, and tunnels, and under this lesson are the plate bearing test, in situ shear test, and other tests. Then the next lesson are the measurements in boreholes and excavations, and under these lessons are the standpipes and piezometers, the extensometers, inclinometers, settlement gauges, and pressure shells. The next lesson is the engineering geophysics, and under this lesson are the geophysical surveys, choice of methods, contaminated land. Then the next lesson are the seismic methods, and under this lesson are the reflection of seismic techniques, continuous seismic profiling, seismic refraction methods, downhole and cross-hole shooting, particular application of seismic methods. Then the next lesson are the electrical resistivity methods, and after that are the magnetic methods, and under this lesson are the electromagnetic techniques, and the last lesson are the gravity methods. So magtaas-taas yun, no? So just be with us, guys. So ang first lesson nga atong i-discuss ron kay ang test in boreholes. Test in boreholes. So sa test in boreholes kay there are many tests conducted in boreholes and are described here under these 4 headings. So the first heading is those that measure the resistance to penetration through the base of a borehole, or the resistance to penetration, the man-made force required to deform the hole, the strength or deformation test, the amount of fluid that can be passed to and from a hole, or the permeability test, and lastly, the natural forces that deform a hole, or the measurement in situ stress. So the first heading is the resistance to penetration, and in resistance to penetration there are 2 commonly used tests, and these are the standard penetration test and the cone penetrometer. So first ato sang discuss kung unsa ning standard penetration test o kung unsa pod nga measurement ang ginagamit ani. The standard penetration test. The test is used for soils investigation. All over the world for the apparatus required is not complex, nor is there any great skill required in the execution of the test. A great mass of experience has been built up justifying its use for foundation design purposes. The test is undertaken at the bottom of a borehole, sunk in soils by methods such as shell and auger boring or rotary boring. So ang kaning standard penetration test, sa pagkondak ani nga test kay dili na siya kailangan og great skill, unya daw ma-master rani nimo siya nga test by just acquiring a great mass of experience. So siguro kanang pag sige na kagamit ani nga test kay kadugyan kay ma-hold na ka. Unya nagsulti po daw diri nga ang kani nga test kay kay gina conduct sa bottom sa borehole ug ginadubong siya. So karon akong ipakita sa inyo ang instrument na ginagamit aning standard penetration test. So this equipment consists of a split spoon sampler or split barrel, which is a sample tube that is split longitudinal into two halves and held together by a screwed coupling and a lower cutting show of all standard of dimension. So ang instrument sa standard penetration test kay first na siya isa ka split barrel. Unya kaning split barrel kay mura na siya tube nga gisuksok sa borehole. Unya ang nagahold ani kay ang coupling to drill rods nga nasa taas dapit ug ang drive show nga nasa may ubos dapit. Unya ang gamit aning vent holes kay para naay sudlanan ug para makasulod gawas ang hangin sa split barrel sa split barrel. This is driven into the bottom of the borehole by an automatic trip hammer, which allows a weight of 622.7 Newton to fall into a drive head from a height of 762 mm. So ang kung makita ninyo sa illustration na siya ang kaning ang instrument daw aning standard penetration test kay gina-duk-duk gamit ang automatic tip hammer. So makita ninyo din na nay hammer na duk-duk pero dili jud siya hammer, representation na para na siya. Unya ang nagaduk-duk jud ana kay ang kaning automatic trip hammer. The number of blows is counted to cause the sampler to penetrate to a depth of 450 mm. So sa pagdukduk sa instrument sa standard penetration test, dapat daw siya musulod og 450 mm into the ground. So the blows sa 450 mm nga depth, ang last 300 mm penetration daw kay described as the N value, and those for the first 150 mm penetration nga diri sa N value kay neglect, being considered to have been in soil disturbed by the boring process. So dire daw sa N value nga sa 300 mm, ang first 100 mm penetration daw kay dili na nila gina-appeal kay although na siyang boring process. So thus on a field boring record, as number of blows would be recorded as 2, 3, 4, 5, 4, 5, giving an N value of 18. So kung atong tanawon diri kung ipang-add to ning 2, 3, 4, 5, 4, 5, dili 18 ang yang value kung dili 3. So ngano 18 man? Diba resulta dito nga sa last slide ang first 150 mm penetration daw kay wala daw siya gi-appeal kay mao na rin siyang soil disturbed by the boring process. So ang kani daw first to reach diri which is ang 2-3 kay wala na siya gi-appeal. So ang N value kay nag-focus ra sa kaning value nga 4545, in which kung i-add na sila mahimo siya into 18. It is essential that the bottom of the borehole is carefully cleaned out, removing any loose material before the test is undertaken. So bago jud ta mag-take ani nga test, dapat sa daw nato limpyuhan ang kaning instrument para assure nga ditso ang work nga atong mabuhat ani nga test. So i-check sa jud ang materials bago ta mag-conduct. So ang next is the end value. So unsa man gamit aning end value? It has been long recognized that end value refers not only the relative density of the sand but also the overburden pressure at the depth of the test. So sulti daw diri ang gamit daw aning end value kay para may bal-an daw nga kung unsa ka dense ang isa ka ground, o para may balan po daw nga kung unsa nga pressure ang withstand sa isa ka ground. So in short, para may balan daw nato nga kung unsa ka lig-on ning isa ka ground, kung put ka rin nakubutan ni siya mga structure. So Gibbs and Holtz 1957 showed that for a sand to have a uniform relative density, end values with increasing overburden pressure. However, at the bottom of the borehole, there is no overburden pressure in the sand being tested, so measured end values tends to be rather low. End values should then hence be corrected. So ang isa daw ka problema aning end value kay sa first record daw aning end value, ang iya daw overburden pressure kay nagkadako. Pero pag mas malalom pa daw ang pagkalot, murag mawala na ang iyang overburden pressure, ug ang iya daw end value tends to be rather low. So in short, dili himo consistent ang ato ang end value. So kailangan daw nato na siya i-correct. So next is correcting the end value. They are generally corrected to relative density or the end value relationship that is proposed by Terzaghi and Peck, which seems to be valid for an effective overburden pressure of the order of 150 to 150 kPa. Smith 1982 was produced graphs to help make the correction. So si Terzaghi og Peck daw kay naghimo daw sila isa ka solution para ma-solusyonan ning ilang problema sa end value. Unya si Smith kay naghimo siya graph para masuportaan daw ning solution nga gihimo ni Terzaghi ni Peck. So mao ni siyang graph kaning sa my right side. So diri atong i-discuss karon kung saan pag-correct sa end value. Assume that the SPT, or the standard penetration test, end values measured in the borehole is 10. So mag-assume daw ito nga ang end value kay 10, and that the effective overburden pressure at the level of the test is 150 kPa. Use the so ang given diri kay nado tay 10 nga end value ug 150 nga kPa or ang pressure niya. So sa N, magbase ta diri sa may ubos tapit sa graph. 10, 20, 30, 40, 60. Dayon sa pressure kay diri sa right side. Then use the horizontal axis and the right hand vertical axis to plot the 10, 15 point. So i-plot daw nato sila by intersecting these two given points. So pag intersect sila, mabase ito ta dire sa mga diri sa diagonal lines, kanang mga lines nga pahiwi-hiwi, and these diagonal lines indicate the relative density, so that the plotted point we will have a relative density of about 43%. Atong tan-awon ang atong na-plot nga point 10 to 50, tapos atong i-record na sila duha, naa daw tay relative density nga 43%. Dayon, using the left hand of the axis, using the left hand axis, draw a horizontal line at 43%. So since nakita naman nato nga ang relative density aning given kay 43%, so gamiton na po nato ning magbase na po ta diri sa relative density sa may left side sa graph. So since 43 man, maghimo daw tag horizontal line din na sa 43 unya until it meets the dashed curve, until daw nga mo sangko siya ng dashed line nga pa curve diya sa sulod sa graph. Dayon ipaba na po nato sa n value, kung unsa nga n value ang masangko niya, mao na siya ang n corrected value. So diri the n value for this intersection is about 15. This is then the corrected n value. So next, atong i-discuss why the n value is corrected. Nganong kailangan man nato i-correct ng n value? Most give n corrected ay so ang n nga ni-correct day kay n corrected na. Most give an n corrected greater than n. N corrected is extensively used in calculating the bearing capacity of unsettlements and sand. So ang n corrected value di ay kay mao dining ginabasihan sa pag-calculate sa bearing capacity bago maghimo buildings ang mga engineers. Then the second point is the alternative methods of correction exist. Many companies issues internal compiled directives to ensure a uniformity of approach in designing the foundation using the n value. So in short, ang n corrected value kay ginagamit sa different companies para daw na ay uniformity sa tanan. Then lastly, n values are corrected in some ways, and Soydemir, isa ka-author, 1987 has described the correction factors applied to the raw n value in New England practice. These factors include allowing for the length of drill rods, the type of hammer used, and the age of the rope used to lift the hammer. So gi-explain daw dire sa last point nga ang n value kay gina correct jud siya para mao na siyang basihan isa ka engineer kung unsa ka tas-on nga drill ang ginagamiton sa isa ka ground, kung unsa nga type of hammer ang ginagamiton sa pagdukdok sa instrument, ug kung unsa pud ang age sa rope nga gamiton para i-lift ang hammer. So kung ato pangitahon ang main idea ngano gina correct ning kaning n value, di ba gisulti man nga ang n value mao na siyang value para maibalan kung unsa kaligon ang isa ka ground. So ang and collected value kay katagag allowance gamay para mas safe ang mga buildings nga itukod anak nga ground. Para bag pasubraan nila gamay para dili kay bugat ang expectation sa pagbuild og mga structure sa anak nga ground. So basta mara siya na guys. So the next test under resistance penetration is the static cone penetrometer. The standard penetration test or the SPT sampler will not give reliable results when the grain size of the granular soil exceeds that of a sand. However, the sampler may be modified by replacing the driving show by a solid steel cone with a 60-degree apex cone. The test is then conducted in the same way as the SPT. So ang kanidawong static cone penetrometer pare-parehara sila aning standard penetration test. Kaso lang kung mabase ta sa structure aning static cone penetrometer sa standard penetration test, ang kaning static cone penetrometer kay naa siya murag pointed nga cone sa ubos. Unya ang gamit ani para maka duot sa ground nga naay mga dagko nga grain size nga type of soil nga mo exceed sa sand. In short, ang kaning standard penetration test day kay dili siya makakayag mga heavy grain size parehaan ng mga sand. Pero og kung yun sa pag-conduct sa standard penetration test, magkaparehara sila sa pag-conduct aning cone penetrometer test katong di bunalag hammer para maduot sa ground. Pero naay disadvantage sa paggamit aning static cone penetrometer. However, if the granular deposits contains grains coarser than gravel size, results can be very unreliable, for the cone may be driving a cobble or boulder down the borehole. The test is not suitable for very coarsely granular materials. So ang kaning static cone penetrometer di ay kay dili siya pwede sa pang very coarsely granular materials or kanang mga materials nga kanang nga grabe grain size kay base sa pagdot daw ani sa ground kay naay masapo nga mga boulder sa sulod sa kuan sa borehole. So maglisod na og duot ang kaning static cone penetrometer kay nanami mga bato-bato sa ubos sa borehole. So mo na siyang disadvantages sa static cone penetrometer. So next is the strength and deformation test. So sa strength and deformation test, there are two commonly used tests of this type, and these are the vein test and the pressure meter test. So the vein test. In this test, a cruciform vein at the end of the solid drill rod is forced into the soil at the bottom of a borehole, generally a shell and an auger hole, and then rotated until the torque on the vein test causes the shell to fail in shear. The test is usually undertaken in places that are too soft or too sensitive to allow the recovery of satisfactory tube samples. So, sa pag-conduct aning vein test, kaning papundak rin siya pag ang soil daw kay humok samaan ng clay daw humok og kana po daw mga soil nga pagbangagan dili siya basta-basta dayon mauli sa iyang natural form. So ang sa pag-conduct ani vein test kay nani siya isa ka handheld instrument nga suksok sa ground, dayon kinahanglan sig tuyok nga una suksok sa ground, tapos kinahanglan sig tuyok. Tapos pag dili na siya matuyok, meaning ana wala na siya resistance. Unya pag wala na siya resistance, dinaan na hindi mo siya ma-record. So ang para mas masabtan ninyo guys, video diri nga ipakita. So
this is vein shear test. We use it for soft material like soft clay. The way it works is we insert blades inside the soil until here, and then we turn this vein shear apparatus and see how much strength the soil has. We use scale. The scale is given here in kPa, and then we look at the results and analyze them. I'll do vein shear test on this soft soil. We put vein shear apparatus in the soil so that blades are covered with soil. We make sure that the scale is set to 0, and then we slowly rotate 1 revolution per minute. There is no more resistance of soil, and we'll check the results. We'll look at the scale. It says 12 kPa. It shows the strength of the soil equal to 12 kPa. Thanks.
okay, so nakita naman ninyo ang video karon diri na pud sa strength and deformation test. So next is the pressure meter test. Pressure meter are cylindrical cells that expand, put pressure on the sides of the borehole and cause the borehole to deform. A pressure meter is constructed measured at the horizontal earth pressure. The pressure meter has two major components. The first component is a readout unit that remains above the ground. The second component of the pressure meter is a probe that is inserted into the borehole to read the pressure. So kung sa vein test kay naa siya isa ka handheld instrument, diri sa pressure meter test kay iyang kabaliktaran. Ang instrument aning pressure meter test kay dili siya dali-dalig gunit. So ang instrument ani pressure meter test kay isa ka dako nga machine, unya naado na siya duha ka component in which ang first component kay mao ni siyang naga-read results, unya naapon na siya sa above ground, ug ang second component kay isa ka probe nga isuksok sa ground ug maupoy sige tulak para pod basahon ang pressure sa sulod sa ground. So ang nadik video diri guys para mas pasabtan pa ninyo kung unsa ning pressure meter test. So next is the permeability test. Values of mass permeability are required to calculate the flow of water into excavations, into tunnels, under dams, and from reservoirs. Mass permeability is defined by K is equal to Q over AI. So ang 3 days sa permeability test kay importante jud day kayo i-calculate ang flow of water ani sa excavation, sa tunnels, under dams, ug sa reservoirs. Unya para makalculate ang flow of water naatay formula where K is the unit of recovery nga na siya unit of meter times second raised to negative 1, and it is measured in the direction of the flow. A is the area at 90% microscopic direction sa flow, ug ang I nag-stand sa hydraulic agent associated with the flow. Unya ang kanang Q sa taas kay constant na siya tapos given. So dili na ta kay mag go deeper diri kay madumalugi na ta. So next is sa permeability test kay naay duha ka mga test nga under ani, ang pumping test ug ang packer test. Pumping test are not undertaken lightly, for they are tests which take days to perform, require the installation of submersible pumps, observation of the fault water levels around the well, made with the help of observational wells, and arrangement to dispose of large quantities of water. Such tests are thus lengthy and expensive, having established a stable water surface with a uniform pumping rate. The permeability of unconfined aquifer is shown in figure 6.3. So ang pumping test, from the word pumping, isa ni siya ka test para either magkuhag tubig or mabutag tubig sa isa ka ground. So sa pumping test po di ay inyong ma-obserbahan diri nga naa siya observation wells. So bago ta himog pump well, kailangan sa ta maghimog observation wells, image ang gamit ani kay para mag-locate kung asa dapit ang naay huge amount of water nga matagpuan sa ground. So kung makita nato diri sa illustration, daghan joy observation wells in which duha kay mura man siya gug trial and error para makuha jud ang perfect spot kung asa dapit ang naay dagay tubig. So pump well kay mao na ni siya ang final borehole or bangag kung asa kuan og naay huge amount of water. So kung mapansin po nyo diri sa sulod sa ground level natay original phreatic surface. So ang meaning aning phreatic kay moist ground, meaning katong wala pa ning kuan pa ning mga pump well o observation wells kay mao nang level sa ay murag di na dapat makita or malocate kung asa ang naay moist ground. So since na naman siya bangag, mao nang ang nahitabuan ng original phreatic surface kay na na slope down ug nahimog drawn down phreatic surface. So mauna na siya. So simpler tests can be undertaken in boreholes, and two kinds of tests are possible. So from diri po sa pumping test kay naa siya pumping out test in which the groundwater table is lowered by pumping and the rate of restoration of the water table back to its original levels is observed. Ug ang pumping in test in which the water is pumped out into the borehole and the water intake is measured. As an alternative to this last procedure, the water head may be raised and its rate of the fall back to its original level may be observed. Then the falling head test. To undertake this test, the section whose permeability is known is penetrated by a borehole. So sa pumping test di kay naa di siya tulo ka buok ka test nga mapili ka kung asa mapilion. Either ang pumping out in which magkuha kag water tapos imuhang obserbahan kung kanus ang mubalik ang iyahang original water level, or ang pang-pumping in test in which mabutang kag tubig sa borehole unya ang water intake or ang pag-absorb sa water sa borehole kay imong measure, or lastly ang falling head test or ang isa ka test kay measure by making a borehole.
Hi everyone, I am Dela Peña and I will start my discussion from measurements of in situ stress. The stresses that exist in the ground before the construction of an engineering work are referred to as the initial or virgin in situ stresses. These stresses are the result of the weight of overlying strata, residual stresses related to the geological history of the ground mass, and the present-day tectonic stress vector. Most in situ stress measurements are undertaken in rock and involve fixing a strain measuring device in a borehole and overcoring device, which then records strains opposite to the stresses existing in situ. The device has mostly to be calibrated in the laboratory in a block of rock taken from the test site. Stress may be measured two-dimensionally by fastening a strain measuring a device at the bottom of a borehole and then overcoring. Devices include photoelastic strain gauges, photoelastic plugs, and electrical strain gauge rosettes. Of this last type, the Lehman doorstepper cell has been widely used and measures biaxial stress in one plane. The Lehman triaxial cell glues 3 strain gauge rosettes to the sides of a borehole, and the strains recorded after stress relief may be interpreted to give the triaxial state of in situ stress. Most in situ stress measurements are undertaken in rock and involve fixing a strain measuring device in a borehole and overcoring the device, which then records strains opposite to the stresses existing in situ. That's referring to figure 6.4. The device is mostly to be calibrated in the laboratory in a block of rock taken from the test site. Stress may be measured two-dimensionally by fastening a strain measuring device at the bottom of a borehole and then overcoring, and that's referring to figure 6.4a. Devices include photoelastic strain gauges, photoelastic glass plugs, and electrical strain gauge rosettes. Of this last type, the Lehman doorstepper cell has been widely used and measures biaxial stress in one plane. The Lehman triaxial cell glues 3 strain gauge rosettes to the side of a borehole. That's figure 6.4b, and the strains recorded after stress relief may be interpreted to give the triaxial state of in situ stress. Tests in large diameter boreholes, shafts, and tunnels. These tests are undertaken to determine the formation and strength characteristics of the ground mass. The sample, tested in situ and contains discontinuities. If useful results are to be obtained, the pressure put upon the sample must significantly exceed the working pressure to be imposed by the proposed civil engineering work. In the book provided, this topic narrates how difficult it is to make the in situ test done credible. For most of the above-mentioned methods, where test is well undertaken, finds it hard being approved. It is because the sample where test is taken lacks of good description, a description that would definitely satisfy its accuracy. Plate bearing test. The test consists of loading a rigid circular or, less commonly, a square plate and measuring the penetration of the plate into the ground. Plates may vary in diameter from about 0.3 meters to about 2 meters. In general, the smaller sizes are used on soils and the larger on rocks. In rocks, larger plates are preferred in the hope that the volume of rock tested will contain a representative sample of the discontinuity pattern in the rock mass. In the figure, the smaller size tests are often conducted at the bottom of the large diameter boreholes so that the plate is connected to the surface by a load-carrying column. The bottom of the borehole must be very carefully cleaned out to ensure that the plate bears on to undisturbed ground. Some type of filler material, generally cement, mortar, or plaster, is placed carefully at the bottom of a borehole to ensure the even transfer of load to the ground. Reaction may be given by a mass of Kent ledge, iron billets, or concrete blocks erected on a frame whose load-bearing legs lie well away from the hole. A hydraulic jack between the column and the Kent ledge is pumped up to press the plate into the ground. In uniformly weathered rock, the objective is to find the depth of the weathered layer which has deformation characteristics adequate enough to fulfill construction criteria. This means multiple plate-bearing tests which may be achieved if the reaction to plate load is given by a cable anchored at some considerable depth below the shallowest test level. Tests on rock may be conducted in tunnels. In such cases, the roof of the tunnel may provide a reaction to the load given by the jack. Tests may also be undertaken across the diameter of a vertical shaft or horizontally across tunnels. Modulus values from the plate-bearing test may be calculated from the formula S is equals to pi times Q over 4 times B times 1 minus V squared over E, where E is the elastic modulus, Q as the pressure applied to the plate, S as the average settlement of the plate, B as the plate diameter, V as the Poisson's ratio, usually assumed to be between 0.10 hard rock and 0.25 soft rock. For tests conducted at the bottom of a borehole, the formula becomes S is equals to pi over 4 times B times 1 minus V squared over E times I sub D, where I sub D is a depth correction factor. In situ shear test. It may be desirable to undertake shear tests on large samples in situ if the scale of laboratory test is too small to give reliable values of shear strength. Such tests may be undertaken on soils or soft rocks in situ, but the most common application is to determine the shear strength of discontinuities in rock in connection with the imposition of inclined loads by dams. The investigation of most dams includes the excavation of trial edits and the shear test made in use roof and walls of the tunnel for the reaction to jacking. It is notable that in figure 6.6, the shear force is directed slightly downwards rather than horizontally. The reason for this is that if the shearing jack is horizontal, the spread of shear stress through the sample is not uniform and failure. That is, the splitting of the sample along the discontinuity, and may begin first near to the jack applying shear stress and then proceed away from it. This may cause the sample to ride upwards near the shear jack, with consequent complication to the test result. The application of slightly downwards shear load may be held to overcome this, but introduces the complication of having to resolve the shearing force into horizontal and vertical components. Other tests. The largest scale test that is commonly undertaken is the pressure tunnel test. In this section of tunnel is sealed off and subjected to internal hydraulic pressure. Diametrically placed extensometers measure tunnel diameter extensions. The modulus of deformation may be calculated with the expression where E as the modulus of deformation, D as the internal diameter of a tunnel, P as the internal pressure, V as the Poisson's ratio, this sign as the diametrical strain at center of loaded length, and this sign as the coefficient depending on the ratio of tunnel diameter to loaded length. If this sign is equal to 1, if loaded length is greater than 2 times tunnel diameter. Measurements in boreholes and excavations. Much instrumentation now in common use has not been in existence long enough to know whether or not it can fulfill all of these requirements, particularly with regard to very long-term performance. With the present advances in microelectronics and computerized systems, it is probably true to say that there is nothing that cannot be measured continually and with great accuracy. Various types of instrument at the site investigation stage may also be used during and after construction for the measurement of a certain geotechnical parameters. For example, pore water pressure. Continuous measurement from before construction, during construction, and after construction constitutes monitoring of the measured parameters. This is where the design optimization, provision of information upon which to base design changes or to confirm design assumptions, and the use of completed structures to monitor performance happens. Standpipes and piezometers. Standpipes consist of a perforated or slotted plastic pipe inserted into a borehole with suitable granular packing or filter material to prevent fine grains of soil from blocking the pipe openings. Water level is measured by a dip meter, which usually consists of twin electric cable connected to a battery and some device, visual or audible, such as light or bell, to record the closure of the circuit when the tip touches the water. The diameter of the pipe is not critical, but it's usually in the range 20 to 50 mm. The system is simple and cheap, but there are two major disadvantages. Firstly, the standpipe can measure only a simple groundwater regime and could not measure pore pressures in different strata because the borehole and granular filter will produce hydraulic continuity between strata. Such a regime may not have existed prior to the drilling of the borehole, and the existence of strata with different pore pressures might very well be critical geotechnical factor which could cause alteration to some fundamental design parameter. Secondly, the response time is often long, especially in low permeability soils. Fortunately, the first disadvantage may be overcome by using a piezometer. Standpipes are used to locate the water table, and the second disadvantage is reduced by using a small diameter pipe so that the piezometer will respond to a lower volume of water flowing into the system. Piezometers. There are many different types of piezometer. The appropriate type is selected according to the circumstances and the requirement. All types measuring groundwater pressure, but they differ in other respects, of which perhaps the most important is response time. The open piezometers are simple, cheap, and effective, provided that they are carefully installed and that their limitations are known and respected. However, there are circumstances where remote reading and a rapid response is essential. For example, where it is necessary to monitor change in pore water pressure under conditions of rapid loading. Such may be the case where rolled clay is being placed for the core of an earth dam, or where the earth dam is being filled for the first time. For such circumstances, a closed piezometer system is required. Extensometers. The simplest type of extensometer is a tape measure which can measure relative movements between structural members such as parts of tunnel linings and sides of excavations. Extensometers measure differential movement. To measure movement of structure, for example, it is necessary to examine movement of the structure relative to the surroundings. Fixed points are established in the structure, and these are monitored by accurate surveying techniques from some distance away. Inclinometers. Inclinometers are used to measure horizontal movements at various levels, usually within earth fields, and may be used to monitor slopes to give an indication of movement within the slope before it becomes visible at the surface. In earth fields, they are often used in conjunction with the magnet settlement gauge. Inclinometers have often been very successful in identifying movement zones and measuring directions, magnitude and rate of movement in both slopes and embankments. Settlement gauges. The simplest way to measure settlement of either the ground or placed field is to grout a reference rod into a block of concrete and measure vertical movement by conventional surveying techniques. This is expensive in terms of manpower, but remote reading, multiple point systems have been developed and are now in general use. Some of these are similar in most respects to vertically installed extensometers. Pressure cells. Pressure cells are used to measure the loads beneath foundations, loads on piles, tensions in ground anchors, loads on the sides of lined and unlined tunnels, pressures within earth-filled surf structures, and so on. As such, some types may be described as load cells. There are many different types, most electronic, but liquid pressure cells record pressure on the sides of a flexible box which consists essentially of two flat steel plates which is transferred by means of contained liquid to a measuring device. Engineering geophysics. Site investigation techniques may be divided into two categories, destructive and non-destructive. Destructive techniques are those which, in their execution in some way, change the nature of the ground they are investigating. Thus, for example, plate-bearing test at the bottom of a shaft test ground influenced by the excavation of the shaft rather than undisturbed ground. Non-destructive techniques examine the ground without permanently altering its characteristics and are generally of either an observational or a geophysical nature. Geophysical techniques fall into two main streams. In the first, naturally occurring phenomena such as gravity, the Earth's magnetism or telluric currents are measured with great accuracy for values anomalous within general trends or reflect local geological conditions. In the second, streamfall methods in which some form of signal is passed into the ground and changes or responses to this signal resulting from geological conditions are observed. Seismic and geoelectric techniques are best known of this group. Geophysical surveys. It may be considered to take place in 5 phases of work. The first of this is the acquisition of data in the field. The second is the processing of this data to derive the maximum value from them. And the third is the preliminary interpretation of the processed data. In the fourth phase, the interpretation is checked against physical observation of site conditions from the results of boreholes, trial excavations, and so forth, perhaps made after the initial geophysical work. The fifth and last phase is the reinterpretation, perhaps after reprocessing of initial data in the light of physical information. The most common interpretation discovers boundaries. Most non-geologists immediately assume that the boundaries are those of a geological body, for all non-geologists are accustomed to looking at geological maps and sections which show the ground neatly divided into distinct, separately colored layers. However, this tidiness is imposed by man rather than nature. All geologists have seen layers or bodies of ground which grade into each other with no clear and distinct separation. Geologists have to make such separations in order to map geological units, but the boundaries used for mapping may be determined by such properties as fossil content, which have no geophysical significance. When geophysical results are compared with records of boreholes, it does not necessarily follow that an apparently incorrect geophysical boundary must necessarily be corrected to fit the borehole record. The boundaries seen geophysically may not be those seen by the eye in borehole samples. This is a figure of an analysis made by Higginbottom, which shows the relative popularity of methods at that time in Great Britain. Choice of methods. In engineering geology, geophysics is used to determine boundary conditions, locate bodies of unusual properties, voids, buried pipes, and etc., or to determine the engineering properties of materials and mass. The choice of method will depend much upon the particular circumstances of the work, which may be not only geological but also environmental. Thus, seismic refraction work using explosives to generate the seismic pulse is unlikely to be allowed in city centers, and magnetometry would be unlikely to be successful in cities due to magnetic disturbances from surrounding buildings, power lines, pipes, and so on. In this area, the investigator must also not assume that only one method is appropriate for a particular purpose. Thus, while seismic refraction methods are relatively useless as a means of finding underground cavities on a site of which nothing is known, they might be able to detect zones of disturbance caused by the presence of cavities in a coal seam whose location is known. Contaminated land. The investigation of buried containers holding hazardous waste, of buried industrial basements abandoned, full of toxic chemicals, of unrecorded drains and slumps used for the illegal disposal of liquid waste, and the existence of contaminated plumes in groundwater at depth, some of which may be floating on the water table, the light non-aqueous phase liquids or LNAPLs, some sinking through water-bearing ground to rest on low permeability layers, dense non-aqueous phase liquids or DNAPLs, are part of the ground that now has to be investigated. Meaning, in this area, geophysical methods are used to help define and quantify these conditions, and their applicability is still being realized. Many techniques in this area can be used. Could be metal detectors for revealing buried metal containers, electrical resistivity for detecting changes in water quality, and also ground penetrating radar for locating trenches in which drains may be located.
So we are now in seismic methods. So sa dili nga method, mag-decrease daw ang seismic waves as they pass through the ground. So ang kalalom daw niya kay mailhan sa seismic geopeaks nga related sa kakusog sa shock na gihatag sa seismic source. So the seismic shocks generates various types of waves. Those of greatest interest are the compression or longitudinal wave, in which the particles vibrate in the direction of wave travel, the shear or transverse wave, in which particles vibrate at the right angle to the direction of wave travel, and the last one is surface waves, which travel on a boundary are distinguished depending on the style of motion of the particle. So kanang compression wave o ang shear wave nana sila formula, which is B sub P equal the quantity of K plus 4 over 3G over P to the power of 1/2. Ug ang formula sa shear waves is B sub S, or shear waves equal the quantity of G over P to the power of 1/2. Where K is bulk modulus and G is shear modulus. So, ang pagkuha sa G kay shear stress over shear strain. Ug ang P is density. Ang ratio sa BP over BS is given ani nga formula. B sub P over B sub S is equal to the bracket of 2 quantity of 1 minus Y over quantity of 1 minus 2V to the power of 1/2, where V is Poisson's ratio for the material. Porous rocks will have fluids or gases in the pore spaces, and velocity through the saturated rock will depend upon porosity and the acoustic velocity of the pore fluid. Media have higher velocities when saturated than when dry. This is indicated by the formula of Wiley 1958. Formula is 1 over V is equal to empty set over V sub F plus 1 minus empty set over V sub M, where V is velocity of the saturated rock and V sub F is equal to velocity of the fluid, and V sub M is velocity of the rock matrix, and empty set is equal to fractional porosity. So, mao ni ang table sa material ug ang ilang compression wave times kilometer s raised to negative 1. Reflection seismic techniques. So, mao ni ang pamaagi sa pagkuha sa mga geophysics na nagagamit og mga prinsipyo sa seismology para matansya nila ang kalalom sa lupa sa atong planeta nga nagigikan sa reflected seismic waves. Continuous seismic profiling. So kani nga pamaagi kay sa tubig ni kasagaran ni sa dagat, ug ang pagkuan sa iyang pamaagi kay kani the hydrophones receive the reflective waves, and after passing through a single channel amplifier or processor, their arrival is recorded on a chart. The pulse is repeated at short time intervals or of the order of 0.2 to 2 seconds depending on the system used. An analog record is built up from the repetitive recording of returning pulses. The record has time as the vertical scale and distance as the horizontal scale to keep the horizontal scale. Uniform, the vessel must move at constant speed. The position of both is monitored by an electronic navigation system, and fixes will be recorded on the seismic record. Such multiple reflection, commonly from the seabed, may make it difficult to identify geological reflectors and interpret the records. Nevertheless, the result may be of great value of particular engineering purposes, such as the location of seabed structures, examination of geology along the lines of undersea tunnels, and so forth. Seismic refraction methods. So, sa mga engineering nga project sa lupa, mao ni kasagaran ginagamit nga method. So, ang pamaagi ani nga method kay 12 or more geophones are used in traverse, while the seismic pulse is provided by explosives, falling weights, or hammer blows. Results are presented in a time over distance, which in favorable condition will show a curve composed of straight line segments with increasing traverse distance and with a sharp segment intersections. The slope of each segment represents a velocity, and it's conventional to designate the velocity of near surface layer as V1, the next velocity as V2, and so on. The depth or D1 to the first horizontal refraction is given by ani nga formula. D sub 1 equal x sub 1 over 2 to the quantity of v sub 2 minus v sub 1 over v sub 2 plus v sub 1 to the power of 1/2. Downhole and crosshole shooting. So sa downhole shooting impulses kay mahimo ni sa ibabaw o sa ilalom sa borehole, o makuha ni sa geophones sa borehole. Katong former nga pamaagi ani kay pwede makahimo og explosives and hydrophones in a mud-filled borehole or on a smaller scale with special pulsars and pickups which can be clamped in small diameter boreholes. Cross-hole shooting. So, duha ka pamaagi ang gigamit ani sa isa ka pagbuto sa seismic kay nahimo ang isa ka borehole na niagi sa yuta para makuha sa mga geophone na nakatanom sa uban pang boreholes. Particular application of the seismic method. Seismic methods have been particularly helpful for assessing rock mass quality, excavability, and the moduli for deformability. Evaluation of rock mass quality. Dapat permi masuri sa ugnayan sa proseso ang quality sa gayon ang kusog nga unweathered rock mass nga naay dako nga space joints kay dapat mag-regard sa high quality with regard to foundation construction, ngunit hindi magandang kalidad hingil sa kadalian ng paghuhukay sa open cut. A significant concept is the idea of the velocity ratio or velocity index. In some older articles, this is referred to as the fracture index. In this, the velocity measured in the field, the rock mass in situ, or VF, is contrasted with the measured in the laboratory on a fresh sample of rock material, or V1. This given the velocity ratio, or VR. So VR is equal to V sub F over V sub 1, which is less than 1. Low in situ velocities, and those low velocity ratios could be due to one or combination of the following factors. Weathering of the rock material. Increasing weathering leads to decreasing velocity. Close spacing of the continuities. The closer the spacing, the lower the velocity. Openness of discontinuities. The greater the aperture, the lower the velocity. Evaluation of excavability. The velocity of seismic waves through a rock mass decreases with increasing weathering and increasing fracture intensity and openness in that rock mass. Experience has been some idea of the velocity of seismic waves through unweathered, normally fractured masses composed of rocks of various types. So, importante may balance sa mga engineering economy whether ang rock mass ba kay drilled and blasted bago i-excavated or i-dug directly with standard excavation machinery. Excavation preceded with drilling and blasting is clearly much more expensive than that without such prior treatment, and important constructual distinction between engineering rock and engineering soil are sometimes linked to the excavation technique.
So, good afternoon to all, especially to you, ma'am. I am Eric Jr. is Esperat, and I am reporting evaluation of the formation moduli. So, in the first slide, the relationship between seismic velocities and elastic moduli expressed by equation 6.11 to 6.13 suggests that it might be possible to determine the static elastic moduli of ground masses through seismic measurements. So, however, there are many reasons why it is necessary to distinguish between statically and dynamically derived moduli, and these are that. So, this illustration shows that the plan shows joint traces in a rock of homogeneous lithology. The joint X persistent, frequent, and sometimes it is open, while the joint Y is impersistent and it frequent. A tan-seismic array would show a higher velocity in direction B than in direction A, thus indicating the strike of the dominant joint. So as you can see, there is a lane between the X and the Y and the direction of A and B between the traverse in a fairway. So the intensity of load imposed by the seismic wave is small, caused by very much smaller strains than that imposed by a large field test, and also by the proposed construction, which are sufficient to large strains. So the seismic wave use sufficient to cause large strains, and use acts for a very short time on the masses, while the load used to measure the static modulus is by comparison applied over long period of time. So it is now well recognized that in continuum mechanics that shear modulus decreases as shear strength increases, and so it has been argued that there are three moduli which can be measured, and the first one is the dynamic modulus, or the E sub dyn, or E sub seis. So determined by seismic means the applicable to low stress level. So applicable lang siya sa pinakagamay na stress levels. While number 2, the deformation modulus, or E sub def, determined by in situ testing on ground masses which do not behave elastically within the chosen stress range. And the number 3, the static modulus, or the stat, determined by in situ testing and measured on the elastic part of the stress strain curve. So the next one is the stress measurements. So it is frequently been observed that seismic velocity change as stress on the rock changes. So in changes in velocity measured by inchoke by cross-hole measurements through the ground, stress by a plate bearing test have been reported by one of the researcher, which is his name is D. Reuter in 1983. So generally, the velocity increases with increasing confining stress until some other change, such as microfracturing, changes the nature of the material also. Attempts have been made to assess stresses in tunnels, mines, mostly in pillars, and by measuring velocities, this appear to have greatest chance of success if this first, the rock is porous. Porous rocks are more sensitive. The rock is dry. Pag ang bato daw kay uga, the rock is homogeneous. The stresses to be measured are no higher than about 50 to 100 MPa. Depende na siya sa type sa rock. Tapos, number 5, variation in external factors such as temperature, humidity, are small. So it has also been observed that the rocks or the soils reach the point of instability. As the result of landsliding or some similar agency, the development of fractures is accompanied by acoustic emission. The one of instability may be detected by arrays, geophones planted at in around of the ground. Acoustic emission also has been studied for at least a half century, for example, by Neil 1968, and it is used in some mines as means of monitoring stability. So kanina mga study ni Neil 1968 nagapakita na ang kaning acoustic emission kay ginagamit ni siya sa pag-test o pag-monitoring sa stability sa mga mining area. So let's proceed to determination of other properties by seismic methods. So in velocities measurements on uniform rock materials give the opportunity to assess changes in materials, properties such as density, porosity, strength, or etc., which might occur as the result of weathering or alteration. So while there are very general relationship between the parameters and velocities of all rocks, velocities measurements are only useful as an alternative to other tests when dealing with a single rock type. So it is possible also that the seismic measurements combined with other tests of a simple nature may give the opportunity to determine or the other complex parameters like the study of Maris in 1982, which has examined the possibility of determining the relative density of sands by a combination of seismic measurements and the particle size analysis as an alternative at the standard penetration test. So the idea is that is not new, but the general relationship between this is the velocity has been established more over the year, and also it has been proved that these seismic measurements are very very important or very relevant nowadays because it opens opportunity to determine or to know the more complex of parameters. So the next topic is all about electrical resistivity methods. So these electrical resistivity methods it is a form of geophysical surveying that aids in imaging the subsurface, and also these methods utilize differences in electrical potential to identify subsurface material. So we all know that all materials have electrical properties, and one of the most important of this is the resistance of the material offers to the passage electrical current. So we all know that copper has low resistance but high conductivity, while rubber has high resistance but low in conductivity. So example, sa groundwater, uh, moderate lang siya og resistance about 50 to 500 ohms meter. But the salt water is more conductive. In pure materials such as iron or aluminum, there are resistivity is in a property of the element. So next slide. So in geological materials, resistivity depends upon the nature and the mixtures of minerals of which the materials are composed of whether or not water is present in pore spaces. So resistivity of clay materials can range between ano kung giyon ganina 50 and 500 ohms meter. Those rich in quartz from 50 to 500 ohms meter also. So if electrical current siya is passed into the ground and the voltage measured between two electrodes, so then the resistivity niya of the ground may be measured. So according to the study of Wenner configuration of in the Wenner configuration of electrodes, current passes between two current electrodes and voltage is measured at two voltages or potential electrodes. So the electrodes line on a straight line and are equally spaced. So mao na perminti ato ang hunaon. The electrodes lie on a straight line and are equal spaced. The apparent resistivity also is given by the formula. So we have this formula. P sub A is equal to 2 pi A times triangle V divided by I. So where P sub A is equal to apparent resistivity, while A is electrode separation, while angle V is change in voltage between voltage electrodes, and I current between current electrodes. So since by Ohm's law, V is equal to Ri, where R is a resistance, electroresistivity is expressed in terms of ohm units of distance. Commonly, these units or ohm centimeter or ohm meter and ohm feet, the most common unit na atong ginagamit karon ng mga panahon na is the ohm meter. Kay maumay dali magamit, ma-convert. So the depth the depth to which the current penetrates into ground of depends upon electrode spacing is the wider the spacing, the greater the depth of penetration. Again, the wider the spacing, the greater the depth of penetration. If the material that the current passes through is uniform to infinite depth, then whatever the electrode spacing will be no change in resistivity. However, if the ground under the electrodes consists of a layered series of materials of different resistivities, then as electrode spacing expand to give deeper current penetration, so will measured. So apparently, this resistivity also changed. So if the material is uniform but saturated below a certain depth, the water table level, then apparent resistivity will also alter as the electrode separation expand. So these curves may be compared with those found in field surveys. To give method interpretation of surface data, unfortunately, several different models may give more or less the same curve, so there is no unique interpretation of result. Normally, additional information is required to ensure reasonable interpretation. This may be obtained from published geological profiles or from boreholes. So, it is possible to calculate the shape of the curve of electrode spacing against apparent resistivity that would be produced from expanding electrode surveys conducted over particular thickness and depths of layers of different resistivity. So, if the basic geology of an area is reasonably well known, then the presence of groundwater may be detected. For this will modify resistivity. So, we're going to the next slide. Magnetic methods. Magnetic methods ta. So, these magnetic methods is The major variation in field strength and polarity direction relate to major continental scale and deep-seated geological colors. So the intensity of the Earth's magnetic field tends to be higher over bodies of minerals of high magnetic susceptibility. susceptibility. So so this intensity so these anomalies are values of magnetic field intensity above or the positive or below negative is the general regional field intensity of area. So minor and local variations depend upon the nature of near-surface geological materials. Iron bearing geological bodies are magnetic and the materials of which they are composed have high magnetic susceptibility. But nowadays, according to my research, that the Earth's magnetic field is generated by electrical currents circulating in its outer core. Values of a total intensity of the Earth's magnetic field vary from about 74,000 gammas. So 1 gammas is equivalent to 1 over 100,000 Oersted at the poles of 30,000 gammas at the equator. So the major variation in field strength, maning ginaingon gana ko ganina, the major variation in field strength is the polarity direction related to the major continental scale of deep-seated geological factors. So, it depends yun na siya sa major variation kung ang field kay unsa ka kusgan og asa padulong ang direction niya. So, nagarelate dyan po na siya. So, also, we're also tanawon po day nato ang size of shape of magnetic anomaly. Size of shape of magnetic anomaly will be due not only to the contrast in susceptibility between a magnetic body, field intensity of the area, because the orientation of the magnetic body relative to the local direction of polarity of the Earth's field. So this magnetic body, also surrounding material, but also due to the orientation of magnetic body, relate Japanese siya sa direction of polarity sa Earth's field. Sabtan, ako kanang basta mao to siya. So ginaingon sila na the strength of the Earth's magnetic field may be measured using magnometers. Old style magnometers measured either the vertical or horizontal components of the Earth's field by measuring the deflection of bar magnets or deep needles. So this measurement such as using the instruments involved leveling the instrument and took some time to complete. So mao tong giingon na kailangan po sa pag-survey nato sa land or pag-survey nato dapat natin mga kinahanglan pod. So in surveying on land most often involve taking proton magnometer readings or intersection of survey grid. So kailangan nato ni no complex calculation is required to convert readings to total intensity values to prepare a magnetic anomaly map intensity values, and also to prepare a magnetic anomaly map intensity values are subtracted from the regional field intensity to allow anomalies to be plotted. So, the greatest part of the work lies in setting out the survey grade. These are the value which monang table which the value of Earth's field varies diurnally, and this should be measured by returning to one stop at regular intervals during the day's work. So, as you can see, magnetic susceptibilities of rock and minerals, or the EMO, is equal to electromagnetic unit for mass susceptibility of m cube kilogram based on Hunt et al. 1995. So, mao ni siya ang mga interval. Average susceptibility of MU, yan, the quartz, calcite, coal, clay, calcoperite, 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 pyrite, limonite, hematite, and so on and so forth. So it is possible to link the detector head to an electronic location finding system to link about the microcomputer, which will then prepare the magnetic anomaly map as a survey proceeds. So we all know then that this magnetometer survey are particularly useful in areas where abandoned mine workings are problem. So, example, the mine workings may have many long abandoned shafts leading to them, and this, if poorly backfilled, may present a localized subsidence problem. These shafts may be no more and than 3 or 4 meters in diameter, and thus presents a target almost impossible to find by boring. So, however, there are sometimes sufficient magnetic contrast between the shaft lining or infilling the surrounding. So, in ano pod sa the effectiveness of the magnetometer pod service may be hampered by local magnetic disturbances, which could result from buried or overhead live electrical cables, buried pipes, wire, fences, and so forth. So there is almost no chance of conducting an effective survey in an urban area. So wala jud chance. Wala jud chance sa mga urban area kay ikaw daw daghan kay tao, pas daghan kay basta ka nang ano kay siya dapat kamo gani siya kuti ang pag-test sa pagkanda. So let's proceed to electromagnetic techniques. So this electromagnetic techniques is the term of electromagnetic techniques applies toward techniques which use low frequently induction. So the description of electromagnetic methods encompasses a wide variety of geophysical techniques and systems. They frequently involve observing the reaction of ground masses to electromagnetic impulses of varying frequencies. Two methods are of frequently used in engineering geology o kabalo jud mo ani na sa gayton pata these are very common, and these are induction methods and ground penetrating radar. So it utilizes electromagnetic induction processes to measure one or more electric or magnetic field components resulting from transient or artificially, and it also generated alternating current sources. Sorry, kay kuan kaya kung lighting dire. So one of example is this illustration. So this illustration, in this cycle, magnetic field is generated by passing alternating electrical current through a wire loop or through a wire grounded at both ends. So, sa pikas o sa pikas pod. The frequency of the magnetic field may be between 100 Hz and about 5,000 Hz. If any conductive material lies within the generated magnetic field, electrical currents will be also generated in it, and this will in the return generate a magnetic field. So diha na siya mag-generate og magnetic field pag ang current niya will be generated pod pag mag-generate pod siya. So as you can see, nagamit din sila, no. So in the field of the equipment, the total magnetic field then existing may be considered to consist the primary field or the generated by the source current. So nag-generate siya gikan sa source current niya, and the induced secondary field which is generated by the conducting body, and measurements of the characteristics of the total magnetic field and interpretation of this. So in the field of equipment may consist on transmitting coil. So transmitting coil in the induction method, and also the transmitting the primary field, and the receiver coil, which is the measuring the total field. Again, when the equipment may consist of a transmitting coil, it means that mag-transmit na siya through the primary field, while the receiver coil measuring the total field. So long wires may take the place of coils. The method may be applied. The method will the method uh, may be up the method may be applied on the ground, example, or from aircraft. Magamit mo naton siya. So these electromagnetic methods, of which there are many, are commonly described as EM methods. So their interpretation of the results often relies upon comparison jud siya sa pag-measured of values with those calculated or observed by the caused by various shapes of conducting bodies. So, nasabtan. The next one is the ground penetrating radar. So, this ground penetrating radar, the basic principle of the transmission and reflection of electromagnetic waves in order to establish the location of airplanes and aid ship navigation is well-known radar. Mao na siya, kuan po na siya, naga-assess or naga-direct po na siya sa radar. Impulses have also some capacities to penetrate the ground and to be reflected from less permeable layers in ways similar to other seismic shock waves. So naga-detect jud siya. So this ground penetrating radar is important jud kay mao man ni siyang kanang signal, a radar signal in electrically generated. It can be repeated continuously rather like than repeated seismic pulse used in continuous seismic profiling. So if both sender signals can be continuously recorded to give a record similar to that received form of CSP techniques, so the radar pulse is reflected from a boundary. So that natay formula which where V effective propagations velocity through the material overlying the reflector, while D depth to reflecting surface, and T elapsed time between transmitted and received pulse. So morning example niya tapos na ni. Wait lang na pa di ay. And also, this formula is V is equal to C over E sub R, where C is also a propagation velocity in free space, and ER is effective relative dielectric constant of the material. So, this typical radar record is shown in the conductivity of the soil and the dielectric constant between the reflector and the surface of the shape of the reflector are factors of the affect performance of the radar. So, this is example. So, nagadetect siya between the water table o sa center sa flank. So, this radiogram, morning radar signal na nakuha, clearly showing in center, flanking, deposits, and the water table. So, yan. So, let's proceed to gravity methods. So, gravity method surveys for such purposes are sometimes described as microgravity surveys, implying at the most accurate instruments are used to make observation on a closed network. So a particular application is finding karst activities in limestone. So the intensity of the Earth gravitational field may be measured in using gravimeters. These are in effect extremely sensitive balance in which the very small movements associated with variation in gravity between successive points of observation are magnified to readability by mechanical or optical devices. So So in this method the intensity of the earth gravitational field may be measured using gravimeters, man akong giyon ganina. There are effects, extremely sensitive balance in which there are very small movements associated with variation in gravity between successive points. So there are theory that or a problem stated that the corrections to the raw data required to isolate the anomalies are often much greater than the anomalies themselves and are difficult to estimate with the required accuracy. Thus, for example, while gravity methods could in theory be used to detect karst on limestone dam sites, this is seldom done because the dam site topography imposes too many corrections of the raw data. So in theory, quite small cavities at depth will give anomalies detectable by modern gravimeters. So by the study of Greenfield 1979, so the method may however it is useful because on limestone coastal platforms which could be the sites for airports or similar construction which must be built on a level ground. So the this problem is or this theory is very interesting because it shows how to detect or how to get or how to conduct in using gravity methods. So that's all, and I hope namoy matunan, and thank you very much, and God bless and keep safe. So there are 10 questions that we prepared to you guys for you guys. So the first question is why it is important to conduct field tests. So our answer is conduction field test is important because there are some tests, especially geological tests, that can't be done inside a laboratory because of coarse grain size that are large to be conducted indoors. Thus, it is needed to be conducted in a field by using boreholes. So the next questions, number 2, what is borehole? So a borehole is a deep, narrow hole made in the ground. It may be constructed for many different purposes including the extraction of water or other liquids such as petroleum or gases such as natural gas. As a part of a geotechnical investigation or environmental site assessment for mineral exploration or as a pilot hole for installing piers rather, or undergrounds. So number 3 questions. What are the different types of tests in boreholes? So there are many different types of tests, but there are four main headlings of these tests. And these tests are resistance to penetration test, strength and deformation test, permeability test, and test in situ stress. So what is the difference between standard penetration? So this is the number 4 questions. What is the difference between standard penetration test and dynamic cone penetrometer test? So the standard penetration test or SPT are the tests that is undertaken at the bottom of boreholes sunk in soils by methods such as shell and auger boring or rotary boring, where the dynamic cone penetrometer test consists of pushing a pointed rod into the ground while measuring resistance to progress. Number 5 questions. What is the difference between seismic reflection and refraction? So in this sense, reflection method is a very sophisticated version of the echo sounding used in submarines, ships, and radar system. Whereas in seismic refraction method, principal portion of the wave path is along the interface between the two layers of hence approximately horizontal. So, number 6 question, what is the working principle of seismic method? So, the basic principle of all seismic method is the controlled generation of elastic waves by a seismic source in order to obtain an image of the subsurface. So, seismic waves are pulses of strain energy that propagate in solids and fluids. So, the next question, number 7, what is seismic refraction used for? So, this seismic refraction method utilizes the refraction of seismic waves by rock or soil layers to characterize the subsurface geologic condition and geologic structure. So, seismic refraction is exploited in engineering geology, geotechnical engineering, and exploration geophysics. So, number 8 question, why seismic method is important? So, the seismic method is by far the most important geophysical technique in terms of expenditures and numbers of geophysics involved. Its predominance is due to high accuracy, high resolution, and great penetration. The widespread use of seismic methods is principles in exploring for petroleum. So, seismic methods are also important in groundwater searches and in civil engineering, especially to measure the depth to bedrock in connection with the construction of large buildings, dams, highways, and harbor service. So, number 9 question. Does ground penetrating radar work through concrete? So, can ground penetrating radar detect through concrete? So, this ground penetrating radar can detect through concrete even if it is reinforced. It can even detect the rebar in the concrete for engineering purposes. So, the next one is, what are the uses of resistivity? So, the uses of resistivity method is useful for simultaneously detecting lateral and vertical changes in subsurface electrical properties. So, electrical resistivity is also used to delineate three-dimensional structures with anomalous electrical conductivities. Oh, manadi ay.